Let's take a look at an example. So in this example, we have a point charge of 5 nanocoulombs, which is at -3, 4, 0, and a line y equals 1, z equals 1, which has a uniform charge density of 2 nanocoulombs per meter. So right away, whenever we see more than one point charge or more than one charge distribution, we should be thinking superposition. And so what we're going to see is we're basically just going to use expressions for each of these two types of charges or charge distributions, and we're just going to add them together to get our total potential in this case. So in this video, we're going to look at only part A, and we're going to come back to parts B and C in the next video. As always with the examples, I encourage you all to pause the video and try to work through it before coming back to the video to see the solution. So in part A, what we're trying to do is we're told that V equals 0 at 0, 0, 0, so at the origin. We want to find our voltage at some point A, 5, 0, 1. Now, there's a couple ways that we could approach this. So if you want to see how this is done in the book, you can look at page 145, but I'm going to do it a little bit differently, and we're going to see sort of the alternate approach as we do part B in the next video. But what I'm going to say is all of our equations from the previous two videos where we had an equation for a point charge and for a line charge, we're using our infinity as the 0 point reference. So let's just say previous equations, and so not necessarily all of them, but just the two previous videos, use infinity as our 0 reference. And so in my head then, I'm thinking, well, it'd be really nice if I could just directly use that instead of having to adjust or go back to a previous equation and sort of adjust that to fit this potential difference as opposed to the potential at one point. And so we're going to see how to do that when we look at part B. But for part A, what I'm going to do to get around having to do that is we can say, let's find VA. So what we want to find is VA with the origin as our reference. So as our 0 potential reference. Well, it turns out that this is going to be the same as VOA, which is, again, A, the notation is different than what we see in our other classes, so this is A referenced to our origin O with infinity let's see if it will stop acting up for me here. So VOA with infinity as our 0 potential reference. And so basically what we're doing is we're just trying to find a workaround so that we can use those equations from the previous two videos. So instead of finding VA, which is what we would have been doing if we say our 0 reference is at the origin, what we're actually going to find is VOA. And that way we can still have our infinity be our 0 potential reference and use the previous equations. All right, so let's come back first to this idea of superposition though. So we know we have a point charge and we have a line charge, so we want to include both of those when we're talking about our total potential at a point. So in general then, for this problem, we can say that our total potential, V sub t, is equal to the potential from our point charge, so V sub pc, plus the potential from our line charge, V sub lc. And so we can go back to our basic definition. So we can say V sub pc is the integral of our electric field due to a point charge dot dl, and then minus the integral of our electric field due to our line charge dot dl. And so we can sort of lean on these expressions that we already have for electric field because we've already analyzed line charges and point charges to get the electric field. So in this case, we can say this is negative the integral of Q divided by 4 pi epsilon naught r, and sorry, no, that is r squared, times the unit vector r, and that's going to be dotted with dr in the r direction because again, That's the only differential link that's going to make any difference because there's radial symmetry for that point charge distribution. And then for our line charge, we're going to have the integral of our rho L over 2 pi epsilon naught rho. And so this is just the equation we had previously for our line charge in our rho direction, dot d rho in our rho direction. Okay, so we can sort of evaluate those two integrals, and we get that our VT in general then is Q divided by, so Q divided by 4 pi epsilon naught R. So just like we saw previously, when we integrate that expression, the R becomes R to the first in the denominator, the negative sign goes away, and we are subtracting from that our rho L, because our rho L is just our constant valued charge density in this case, so there's no spatial dependence, divided by 2 pi epsilon naught. So now when we integrate this 1 over rho, recall that the integral of 1 over rho is going to be log of rho, so we multiply this by natural log of rho. So here is our equation for potential at any point located by R. So for potential at any point R, and so, well, let me say this a little differently. So at this point, R is going to be the distance from our point charge to our point of observation, and rho is going to be the perpendicular distance from our line charge to the point of observation. So rho is perpendicular distance from our line charge. And so that's very important to note, because that means that both this R and this rho, and so I realize that R looks like a sigma, so let me write that a little bit better. So our R and our rho are both locally defined. And so this is something we've talked about before. It's very important as we're dealing with all these various configurations. So what locally defined mean is, of course, this line charge is on the line y equals 1, z equals 1. So rho is the perpendicular distance from that. It is not the perpendicular distance from the z-axis. So similarly, our r is not going to be the radial distance from the origin. It's going from our point charge, wherever it may be located. In this case, it's at -340 to our observation point. So very important that you understand the difference there between locally defined versus globally defined. Okay, so now that we have this general expression for our total potential, we want to find the appropriate R and rho for our origin in A. So want to find R, goodness, all right. Well, let's see if I can get this to cooperate. So we want to find R and rho for our point A and for our origin point. So O and A. So let's start by looking at our origin. So for our origin, we can say that the distance R naught from the point charge to our origin. So remember, our point charge is at -340. So from the origin, the distance is the same as the magnitude of the distance vector to that point charge, which is going to be -3 squared plus 4 squared. All right, come on. Plus 4 squared plus 0 squared. And so if we evaluate that, we get that that is 5. And then for our rho, so remember our line vector is at y equals 1, z equals 1. So for perpendicular distance to the origin, we want to evaluate that where x is equal to 0. So we're going to say the distance is the magnitude of the difference of the two position vectors. So for the origin, our position vector is 0, 0, 0. And for our line charge, again, if we want perpendicular distance, we want it to have the same x value and 1, 1. So magnitude of that is going to give us square root of 2. So now we can figure out the potential at our origin. So we can say the potential at our origin, and remember this is using infinity as our zero potential reference, is equal to the magnitude of the point charge, which was 5 nanocoulombs, so 5 times 10 to the minus 9th coulombs, divided by our 4 pi, and then our epsilon naught, which I'm going to write as 10 to the minus 9th divided by 36 pi. And then we have our r, which we found up here to be 5. And then that is all for our point charge. So now we need to consider our line charge. So we have our charge density, which is 2 nanocoulombs, so 2 times 10 to the minus 9th per meter, divided by, so we have our 2 pi epsilon naught, which again I'm going to write as 10 to the minus 9, divided by 36 pi. And now we have log of our rho, which we found to be square root of 2. So if we plug that in, we get 9 minus 36 log square root of 2. And so I'm going to come back and we're going to simplify that and put an actual decimal value in our final answer. So I didn't show explicitly, but there are of course several terms here that cancel out. So the benefit of having that e in that form is that 10 to the 9th from our nanocoulombs is going to cancel out there. In this case, we have the 5 canceling out. We also have our pi's canceling out here, and we have our 2's canceling out here. So we have a lot of stuff sort of canceling out here is why we left it in that simplified form. Okay, and so again, this is with infinity as our zero potential reference. All right, so now we want to do the same thing for our point A, and then we're just going to take the difference of the 2 points to get the voltage difference between them. So at point A, we have RA is equal to the magnitude of the difference of our 2 position vectors. So our point A is located at 5, 0, 1. So that's our position vector for point A, and then our position vector for our charge, our point charge is -3, 4, 0. So if we take that difference and find the magnitude, it ends up being 9. And then our rho for A is equal to the magnitude of our, so we want the perpendicular distance from that line. So we have our point is 5, 0, 1. If we want the distance to be perpendicular, we want our x value on the line to have the same x value as our point. So we have 5, 1, 1. So magnitude of that difference gives us a value of 1. All right, so now we just plug those into that general T equation, and we have VA is equal to, so we have our point charge, 5 nanocoulombs, divided by our 4 pi, 10 to the minus 9th over 36 pi is our epsilon naught, and now in this case our R is 9. All right, so that's for our point charge. For our line charge, we have the 2 nanocoulombs per meter, so 2 times 10 to the minus 9th, divided by 2 pi, times our epsilon naught, which is 10 to the minus 9th over 36 pi, and that's now multiplied by log of 1. So because we had that natural log of 1, this whole second term is going to be going to 0, and over here we can see we have the 10 to the 9th canceling out, the pi canceling out, the 9 is going to cancel out with this 36 over 4, and what we're left with then is just 5 volts. And so the units up here were volts as well, so I left that off. So now, as we sort of said in our initial game plan, remember we sort of changed around what we were looking for. We wanted VOA, which is a reference to our origin. And so now that we have VO and VA, we can find that. So we can say our V of A reference to our origin is VOA is equal to VA minus VO, which is equal to 5 minus 9 minus 36 natural log of the square root of 2, and we get that is approximately 8.477 volts. So that is the answer for part A. And again, if you want to see how that's done without using infinity as a reference, the zero potential reference, you can look at page 145 in the textbook, but we're going to use a similar method as we saw for part B in the next video.